What if the future of computing didn't run on electricity at all? What if it ran on light? In the race to make quantum computing a reality, one technology is shining brighter than the rest: photonic quantum computing. It's not just a lab experiment anymore. It's moving onto real, integrated chips that work at room temperature, connect natively, and are built using decades of optical manufacturing expertise. Today, we'll explore the breakthroughs, the key players, the challenges, and the roadmap ahead, and see why light itself might power the future of computing. So what exactly is a photonic quantum computer? Instead of electrons, it uses particles of light, photons, as quantum bits or qubits. These photons carry information in their polarization, time bins, or even in continuous properties like amplitude and phase. And here's why that's exciting. They run at room temperature. No massive cryogenic freezers required. They have incredibly low decoherence, meaning they can hold quantum information longer and travel long distances without losing it. They come with built-in connectivity. Optical waveguides and fibers make it easy to link qubits together across chips or even cities. And the fabrication process is mature. The same tech used for photonic integrated circuits can now build quantum chips. There are two main ways these computers work: gate-based circuits, using linear optics, non-linear interactions, and feedback, or measurement-based computing, where huge entangled cluster states of photons are measured step by step to run algorithms. Since 2025, the technical breakthroughs are coming fast. First, integrated cluster states on silicon photonics. Peking University created the first on-chip continuous variable cluster states with squeezed light sources and waveguides all integrated. This means powerful quantum logic without bulky lab setups. Secondly, deterministic single photon sources, quantum dots in microcavities, now hit 71% efficiency and 98% indistinguishability, crossing the threshold needed for error correction. And finally, high-efficiency detectors and low-loss components, superconducting nanowire detectors, now exceed 98% efficiency, while modulators and waveguides have record low losses, shrinking the size and boosting the performance of photonic processors. So who's leading the charge? PsiQuantum, with $700 million in funding, aiming for 1 million qubits with CMOS-compatible circuits. Xanadu, known for its Borealis platform, now scaling up to a modular network called Aurora. Quix Quantum, Europe's leader in low-loss processors, selling to research powerhouses like the German Aerospace Center. Quandela, hybrid spin photon qubits, slashing the resources needed for fault tolerance. Photonic Incorporated, building spin photon interfaces for distributed quantum networks. But we're not there yet. Photonic quantum computing must overcome several obstacles before realizing large-scale universal processors, including resource overhead is still high, even with better photon sources. Further reducing optical losses and improving on-chip multiplexing are critical to efficient scaling. While the photonic circuits themselves run at room temperature, leading emitters and detectors still require cryogenic environments. Seamless integration of these modules poses engineering and cost challenges. Integrating detectors directly onto chips is tricky, and deterministic 2-qubit gates, the key to full universality, remain a tough nut to crack. Photonic quantum processors aren't just about computing. They're transforming quantum communications with all photonic networks. They're accelerating AI research with quantum machine learning. And they're showing quantum advantage in boson sampling experiments that classical computers can't match. The next few years will decide if photonic quantum computing can scale to universal machines. Key milestones include fully monolithic integration, embedding sources, waveguides, modulators, and detectors on a single chip to minimize loss and simplify fabrication, reducing error rates below 10 to the power of -3 for 2-qubit gates. Developing architectures that combine cryogenic photon generation with room temperature photonic circuits, lowering the barrier for deployment. Launching accessible photonic-based quantum accelerators for materials science simulations, secure communications, and AI workloads. From research labs to manufacturing foundries, photonic quantum computing is lighting the way forward. The question is no longer if it will work, but how soon it will change everything.